All right, good morning, everybody. Sorry, I'm a little late. But we're gonna jump right in if my computer cooperates.
Good morning.
Having some tech issues. Let's see if we can get it together though. Come on, bruh. Man. Just need to install this plugin right quick so I can share my screen. I'm not sure why it got deleted the last time I did it. It's coming up though. All right. So let me make sure this is recording. I don't need something else to go bad. Yes. All right. So we're gonna pick up where we left off on Wednesday, which is we were talking about drawing mirror images and determining configuration, and we did the mirror image and configuration for the Fisher projection. We talked about how if the hydrogen on a Fisher projection is horizontal, you change the configuration once you assign it, and then how if it's vertical, you keep it. So let's do this example down here. And let's start with this stereo center right here. Right, so we've already drawn the mirror image. I have a methyl group here. I have one here. And then an aldehyde. And then this carbon right here. So if I prioritize those, which one do you think is going to be one? Right here you have, you got a carbon here, and all three of your groups here are carbon, right? But the carbon, where the alcohol is right here, has, sorry about that, one bond to oxygen. Right, and then this carbon has two bonds to oxygen. Right, so this carbon down here is going to take higher priority over the other one. So this is going to be one, this will be two, and that'll be three. And then the fact that the aldehyde is on a wedge, that means that the hydrogen that's here, the other group that wasn't shown, which is a hydrogen, is on a, I'm sorry, the aldehyde is on a dash. So that means the hydrogen is on a wedge, right? And we know that's always going to have the lowest priority. So how are those groups? Go ahead.
Y'all connected the couch?
All right. All right, so how are those groups oriented? If the aldehyde is one, and the OH, the carbon where the alcohol is two, and then the methyl group is three, is that clockwise or counterclockwise?
Counterclockwise.
Counter. But remember the shortcut we learned the other day, if that hydrogen is on a wedge, it's not back, and we're going to reverse it, right? So the fact that it's counterclockwise means that it would be what?
It would be S, but
S. But since H is wedged, then we're going to make it R. So this stereocenter right here, this is going to be R. All right, let's do the next one, and then we'll move on to another example. All right, what do you think about this stereocenter right here? Let me change the color of my highlight. Which group is going to be 1? All right, you have a hydroxyl group,
Lauren.
oxygen, you have a carbon on that side, and you got a carbon on that side. Is that right? And then it's understood that there is a hydrogen here on a wedge, right? So if I were prioritizing that, what would you say? Which atom is going to be 1? Oxygen or one of the 2 carbons?
I think the carbon, because the one that's connected to the chlorine would be 1.
No, okay, that's a good assumption, but the oxygen has a higher atomic number, and we only care about the atom that's bound directly to the chiral center. So the oxygen here is going to be 1. And then the 2 carbons to the left and to the right, this one is going to be higher priority because it is bound to chlorine, where the one on this side is bound to another carbon. Are y'all following that?
Yes.
So that is 1, 2, 3. It looks like it's clockwise. But because hydrogen is on a wedge, we're going to reverse it. So normally it will be R, but we reverse it because of the wedged hydrogen. So we're going to call it S. All right. Now let's look at the last one. And if we prioritize, obviously chlorine is going to be 1. And then you have 2 carbons on either side, here and here. 1 carbon is bound to oxygen, the other one is bound to hydrogen. Which one do you think is higher in priority?
The one bound to oxygen.
Good. So that's 2, and that's 3. And that looks like it's also clockwise because there's a H, but it's dashed. There's a hydrogen back there that's not shown. So this is clockwise and H is already back. So the configuration of that is going to be R. All right, questions about that? So the configuration, total configuration here is R, S, R. What would the configurations be for the enantiomer, the mirror image, that mirror image that we have drawn on the other side?
SRS.
Yes, they have to be the exact opposite. That's exactly right. So this would be S, R, R, and then that would be S. The enantiomer is always the exact opposite, right? It's whatever the original image is, the mirror image will be the exact opposite. All right, let me ask, what would a diastereomer of the original image look like? If I ask you to draw, let me go back up here where it is. If I ask you to draw a diastereomer of this image, what would it look like?
Wouldn't the wedges be dashes and the dashes be wedges?
Well, that would be the enantiomer if we changed everything. Remember, the diastereomer is not a mirror image. So we would only have to change 1 of the 3 to get a diastereomer. So if I made that wedged, right, and then kept the other 2 the same, that would be a diastereomer. That's sloppy. You following? So the only thing I changed is this. So the dot, keep in mind the diastereomer is not a mirror image. All right. What about ask you how many stereoisomers were possible for this molecule? What would you say?
Three.
What's
Wouldn't it be 8?
8? Good. What? How did you come to that conclusion?
We have 3 different stereoisomers, so 2 to the 3 is 8.
Yeah, you got 3 stereocenters. So you use that formula 2 to the n, and we plug in the number of stereocenters in that formula. So you get 8 total. Good. All right, let's go to, we've already done 2 already and 3. Yeah, because we've done the configurations, we've drawn the mirror images. The only one we haven't done is this one. So let's go ahead and let's do this one. I think I cut it already. Just didn't get to it the other day. So we drew the mirror image. What's the configuration of this stereocenter? Right, let's pick out the groups. Right, you have an oxygen bound to it. You got a carbon, and a carbon. All right, what do you think? So we need to be able to apply that the Kahn-Ingold rule to figure out which carbon is higher in priority. Right, we know oxygen is going to be 1. So of those 3 carbons, which one do you think is highest in priority?
The double bind.
The one double bonded to oxygen. Very good. That's 2. And then of these 2, here and here, this one is bonded to oxygen. This one is bonded to nitrogen. Oxygen has a higher atomic number. So that's going to be 3. And then the cyanide is going to be 4. It doesn't matter that it has 3 bonds to nitrogen, right? If it was compared to another carbon bonded to nitrogen, then it would matter. But the fact that it has 3 bonds to nitrogen does not matter. It's bonded to nitrogen, whereas the carbon up top on the vertical line is bonded to oxygen. So that's going to precede it. So what do you think? Is this, what's the configuration? What do we need to do? Since it's a tetrahedral, we need to draw it in the steering wheel. Am I right?
Yeah.
So that'll be here. The OH is going to come here, and I'll explain, and then this will be here. So if I turn it this way so that the cyanide group is facing away from me, do you see how like it's the axis is here? Right, there's an axis through there. If I just rotate around that axis to get cyanide pointed away, this is how the groups will be oriented. So that'll be 1, that's 2, and that's 3. Anybody not see that? Then that's going to be counterclockwise. So it's S. Any questions on that one? So we want to put it in, when you have a tetrahedron like that, you want to put it in the steering wheel so you only see the top 3 groups. What about the enantiomer? What do you think? What's the configuration on that one?
R.
It's got to be R, right? Because it's the mirror image. Let's see a bunch of. All right, it's got to be R. That's exactly right. All right. Now let's go down. I sent you a video the other day dealing with how pre-existing stereocenters affect the reaction, the outcome of a reaction. So we're gonna look at this reaction right here, which is, anybody recognize these reagents from part one? Hydrogen peroxide and sodium hydroxide, anybody? I'm gonna cut this out and put it on a separate page so we'll have room to work with it too. So let me do that right quick. And then we got
Is
another
it an
part.
acid-base reaction?
Say again?
Is it an acid-base reaction?
Somewhat, but not quite. Put a blank page up back here and date it. All right, let's look at it. Let's see if we can work through this. It's actually,
Is it hybridization?
ooh, not quite. It's actually an epoxidation reaction. It's an epoxidation. Let me fix my letters too. They'll be talking bad about me on Twitter. Oh, that's not much better. Right, remember from organic one, when you take an alkene plus hydrogen peroxide and sodium hydroxide, you get an epoxide, a cyclic ether. Y'all remember that? Anybody? If you
Kind of.
took my class, you should, because we talked about this quite a bit. And we talked about how to open them up too. All right, so that's and let me put the carbons in so you won't get confused about that part. All right, so this is just a simple alkene. If you treat it with hydrogen peroxide and sodium hydroxide, you get an epoxide. And then these carbons are still here. This is CH2 and that's CH2. All right, that's a reaction that we learned in part one. All right, so one of the ways to, let me put that up here. It's the 20th. Man, this month is gone. We're going to talk about this now, ways to induce chirality. My finger is not working today. Right? There really are two ways to do this. Right? One way is to use a chiral catalyst to run a reaction. Russell, get your mind right. Right, so some reactions you do them in the presence of a catalyst that has some chirality built into it. And one example of that, like, would be like a cobalt catalyst. Let me just show you an example. So you have a cobalt, and then on that cobalt, you'll have that coordinated to a ligand. And you don't have to worry about writing all this out. I'm just showing you. It would be, the metal would have a ligand around it. This particular ligand is called a box ligand or bisoxazoline. Right, a bisoxazoline ligand. So that is an example of a chiral catalyst where you take a metal like cobalt, you add a ligand to it, and you create like a chiral space around it. And then when the reactants bind to the ligand, right, they can only bond a certain way, right? So the ligand creates like this bifurcation where you have one pathway that's going to be lower in energy than the other, and then the low energy pathway usually predominates, and that's the product that you get the most of, right? The other way to induce chirality is to use a pre-existing stereocenter, or use a molecule with a pre-existing stereocenter. All right, so pre-existing chiral center. That's the other way to do it. What happens when you use that strategy is we get out an unequal mixture of stereoisomers. All right, let me add actually, you know what? Let me move this. All right, so when you use a molecule that has a pre-existing chiral center, what happens is you get out an unequal mixture of stereoisomers. So you react something. Anybody remember this from that video? Chiral plus achiral. You're going to get an unequal mixture of stereoisomers. And then if you take two achiral things and mix them together, what do you get? What's the term used to describe the mixture?
Racemic.
Racemic.
Mixture.
Good. Very
Racemic
good.
mixture.
You good. You good. You good. You're right. You're 100% correct. You get a racemic mixture. That means you get 50% R and 50% S, right? In equal amounts. Right, 50% R, 50% S. And so again, why does this matter? If we go back to something like Taxol, it matters, right? That you're able to do a reaction and do it enantioselectively so that you get out one stereoisomer, or you get out of you're able to isolate one stereoisomer. There are ways to do that too, right? You can isolate stereoisomers using chromatographic methods. You can use HPLC. Depending on if it's enantiomers, you have to use something like HPLC to separate them. If it's diastereomers, then you can use a physical method like column chromatography. But that's beside the point. The thing is, this is like the holy grail for organic chemists, to be able to make molecules with chiral centers and make them selectively. Like that's the holy grail of organic, because all of these all the natural products that you see that are chemotherapeutic, that have antiviral, that have biological activity, things like that, many of them have multiple chiral centers, and the only stereoisomer that works is the one that's found like in nature, right? The mixtures don't work. So if you're doing a reaction, you're trying to generate chirality, you don't necessarily want it to be a mixture. You want it to be enantiomerically pure. So you want one isomer over the other. So that's the purpose of doing this type of stuff. And many of your pharmaceutical companies, that's why, drug development is such a powerful industry, because a lot of what they do is simple reactions like this, where you have to come up with a way to make, one enantiomer over the other. They don't do it one reaction at a time, though. They use a lot of combinatorial synthesis. where they just run, they may run 100 reactions all at once, test each well in a 96 well plate and look for that product. And then if they find a hit, then they go back and optimize it. So when you have a pre-existing chiral center like this one, right, where you have a chiral center right next to your reactive site, that's going to affect the outcome, because this is an example of taking something chiral plus something achiral, which would be your hydrogen peroxide, and reacting them together. So you should get out, based on that concept of chiral plus achiral equals an unequal mixture, you should get out 2 stereoisomers, but you should get one in a higher percentage than the other. All right. So let's look at the reaction, and I'm gonna take this. I'm gonna copy this. I know I'm gonna run out of room. All right, so this is my reaction. Let me ask you a question. When I make the epoxide, you don't have, this is not a right or wrong answer, but I just want to see how you're thinking. When I make the epoxide here at that double bond, right? What are my 2 possibilities for my product? Look at the chiral center. It's on a wedge, right? What do you think? If the chiral center is on a wedge, and we look back at the epoxide up here, let me show you that again, right? What are the possibilities for these bonds right here? They can't be opposite now. They got to be both either wedged or dashed. But what do you think? I could easily get this epoxide or this epoxide, right? So let's go back down to here. What do you think my 2 products are going to look like? Right, this is not going to change. But on that, on carbon 2 and 3, now I have an epoxide. So I'm going to draw one of them where the bonds are dashed. Right. And then I'm going to draw a second one, the second product that's possible, with those bonds on wedged. Are y'all following that or no?
Not really. No.
So the epoxide itself, right? If I take that double bond and react it with hydrogen peroxide, I'm going to get an epoxide, period. It's going to be a cyclic ether, right? That reaction is, the outcome of that reaction is like, it is what it is. You're not going to get another product. It's not going to be alcohol. It's not going to be some type of carbonyl. You're going to get the epoxide, right? That's the outcome of the reaction. But when you have the stereocenter here next to that reactive site, right, it's going to actually force the oxygen to come in from either one side or the other, right? So let me So let's think about this in terms of, everybody remember this term from part 1, what a transition state is? Can somebody tell me what that is? Anybody? Like if we're doing a reaction, let me just put a diagram here. We got a reaction energy diagram like this. Where would the transition state be on that diagram?
Wouldn't it be in the mid, like right in the middle?
Right here?
Right? Yeah.
Like the peak side.
Yeah, it's the highest energy point on the energy diagram. What does it mean though, when you have when you're saying that you are have a transition state. What does that mean? Anybody?
Isn't
remember that?
That when it transitions from like gas to liquid or
No,
or
not
from to a product?
Isn't it when like I was gonna say like when the excess or whatever, like afterwards you only gonna have excess leftovers, like when you use all the reagent or something like that.
So when the reactants start getting together, right? That's what it is. So you start breaking bonds and making bonds. So the transition state is the highest energy point where you have some bonds in the reactants being partially broken, and then you have some bonds that are going to be for the product being partially made. So in this case, like when the transition state, and I'm just approximating this because I don't know exactly what it would look like. The transition state here, right? You'll have oxygen coming in, right? And that oxygen is going to be partially bound to one of these carbons, and one of these carbons is going to be partially bound to oxygen. And then you'll have a partially broken OO bond. So this would be forming, that would be forming. Right? So that's what the transition state would look like for this reaction, where you have partially formed bond between oxygen and carbon on each side, and then a partially broken bond between oxygen and the other oxygen in the peroxide. But the point is, this group right here is going to dictate where that oxygen can come from, right? It's either going to come from the same side that the group is on, or from the opposite side. So the fact that it's on a wedge, if I try to bring, and keep in mind that tert-butyl, that's a very big substituent. If I bring that in from the same side, so I bring my oxygen in from the same side, do you think that's good or bad? And this was in the video that I sent, but do you think that's low energy or high energy to bring a substituent or a group in from the same side in the same direction where that substituent is already pointing, and it's chiral, so it's fixed?
Hi.
It's going to be high energy, so that's bad, right? So in order for oxygen, so oxygen came from the same side, that would be, let me see if I can get this up some. That would be this product right here. You agree?
Yes.
Because the tert-butyl is on a wedge, and then the oxygen is also on a wedge. So this would be same side attack. All right. And then if the oxygen came opposite of the tert-butyl, this would be the product.
And that would give us lower energy, right? If it comes from
Yes.
Okay.
Higher energy. I'm gonna just say delta G, and then this will be low delta G, right? Which is good. In chemistry, you always desire the lowest energy pathway. That's going to be your fastest route to forming product, right? So which one do you think is going to be present in the highest amount? Is it going to be the one that costs you $1 million to get, or is it going to be the one that costs you $10 to get?
$10.
Yeah. It's just like real life, right? You got $25 in your pocket. You're not going to go buy, if you need a pair of shoes, you're not going to go buy a pair of Jordans that cost $200 because you can't afford them. You're going to go to Dollar Tree or wherever and get you some slides until you get your money right. And so these, with this substituent right here, if the oxygen attacks from the same side, then it's going to cost more energy. And that means that that pathway is going to be lessened because it's going to be harder to get to that product. All right, let me write that down here. Oh, somebody calling me, they know I'm in class. Usually Fridays are easy, but not today. Right, so same side attack is going to be higher energy. So the desired outcome is for the energy to be lower, right? So you really got two competing processes here, right? Front side attack and back side attack. So this opposite side attack is going to be what we call a major product. And then this one will be the minor product. Major meaning it's present in the highest amount, minor meaning it's present in a lower amount. Are we okay with that? We're on the same page with that? Now I know this is a lot to write down and process, so feel free to ask questions.
I have a quick question.
Go ahead.
Can you remind me about the transition state situation? I
Yeah,
know-
sure.
Thank you.
So let's say we have, let me find a blank page. Yeah, let's say we have A adding to B, and that's going to give me C, right? So at some point, if we look at it from the perspective of an energy diagram, these are your reactants, these are your products, this is the transition state. So in order for A and B to get together, they got to like share electrons, they got to collide. And when they come together, let me not even say C. Let me just say AB, because you got a bond between them, right? So as A and B, let's say A has the electrons and B doesn't, right? So as A starts to share electrons with B, all the way up this path, at some point, right, the bond between A and B starts to form. Right. And so that's where you are right here at the transition state. That's when your bonds are being formed, the bonds are being broken. Right. And then from the transition state to the product, it's just exactly what it is. It's the formation of that bond, the finalization of that reaction going from transition state to product. And then, of course, if it's exothermic or endothermic, that matters too, right? Because you have like, when you think about the Hammond postulate, if it's exothermic, then by the time you get to the transition state, that looks more like the reactant than it does the products, because it's an early transition state. And then if you think about it being endothermic, then that transition state for an endothermic reaction is late. And so that's going to look more like the product than it does the reactant. So the bond formation will be more extensive. So it just depends on whether it's exo or endothermic. But the point is that in the transition state, that's where the terminology is kind of descriptive of what's happening. There's transition happening. So your reactants are coming together to become more like what you're trying to make, your product. So they're transitioning from their original state to what they'll be on the other side of the reaction arrow.
Thank you.
Yeah, great question. And this is all like thermodynamics. So it's more physical organic chemistry, but it's still good to know. All right. Any questions about this reaction up here? Let's see if we can answer these questions now. So we see what the reaction is. We see what the outcome is. We see what the two products are. This is when you have a mixture like this and you have a ratio of one product to the other. That's called what we call a product distribution. right? So it's not just one product. You get two products in a certain percentage. It's called a product distribution. So let's answer these questions up top, and then we got to stop. So which one do you think is favored based on what we drew down there? And let me just draw. I'm gonna draw them both back here, but I won't draw the whole thing. So it's this, and then I'll just abbreviate that. And then is this. Which one do you think is going to be favored?
Would it be the major product?
The major, yes. The one that's where the with backside attack. That's exactly right. So this is favored. All right. And then it says, what do you think will happen if we change the tert-butyl to a methyl group? So we make it something smaller. What do you think will happen to that ratio of major to minor? Let's say you get, let me put some numbers in down here. Let's say you get 85% of this, and these are arbitrary. So, and 15% of that. What do you think is going to happen to that ratio if I make the substituent, the chiral substituent, smaller?
It'll be more even.
Yeah, you're going to get more of that minor product, aren't you? Right,
Yeah.
you'll get more of the same side product if that's a smaller substituent, because the energy to get to it is less, right? What in the video, there are two things that kind of govern these reactions with pre-existing stereocenters. What are those two concepts or two principles? Anybody? Size is one, and proximity is the other.
By size, you mean mass?
Yeah, no, not mass, physical, like steric size. So like you see, this is a tert-butyl. If I take that and on the other example, we'll look at that Monday. We're going to talk about that more. But if I make the tert-butyl into just a simple methyl group, that means that the bulk of that actually decreases, right? And then proximity means just location. If it's closer to the reactive site or if it's further away. All right, so if I change the tert-butyl group to a methyl group, right, the ratio of stereoisomers is going to go down. So instead of 85 to 15, it might go down to 75 to 25 or something like that. And then the other question is based on this other piece too, the proximity part. What do you think will happen if you move the tert-butyl all the way down to carbon 6?
The ratio go down.
It's going to go down too. It'll have the same effect. Making it smaller or moving it further away from the reactive site both have the same effect, which is they allow for that high energy pathway. They allow more access from that pathway. All right, we got to stop here. We have another question on this handout that we're going to work through, and then on Monday we'll hit this, and then we're going to jump and start another topic. All right, any questions about anything? I know I'm about 5 minutes over.
Quick question.
Go ahead.
For the quizzes that you posted, do we just complete them over the weekend?
Yeah, you can. Those were, I didn't have them unlocked, but those were the quizzes based on the videos that I've sent out so far.
Okay.
Yeah.
Okay, I was just making sure.
Yeah, you good. Just take them. And if you don't, even if you take them over the weekend, if you take them Monday, it doesn't matter as long as you take them before the exam.
And what was the proper names for those videos? I know one was stereochemistry, but then like two of them kept saying enantiomer.
Yeah, enantiomers and configuration part 1 and part 2.
Okay, understood.
Yeah.
Do you have a video showing how major and minors are forming?
I sent it already. I sent it yesterday.
Okay, thank you.
Yeah, it's in the announcement from the link to it is in the announcement from yesterday. Right. Any other questions about anything?
Dr. Russell, this is Autumn Anderson. I sent you an email, but I never got a reply.
Let me see. When did you send it? Yesterday?
I think it was Monday or Tuesday. But I was just letting you know you can reply to me when you get a chance.
All right. Let me look. That was Wednesday. Yeah, I emailed you back, I think. Oh, it's still in my drafts. My bad. There's a folder. If you go in Blackboard, there's a folder in the either in course documents or it's in supplemental handouts. There's a whole folder full of stuff in there from Organic 1. And
Okay,
I intended
thank
to,
you.
yeah, I intended to send you the link back in the email. I probably got distracted and forgot to hit send, but there's a whole folder in there.
Okay, thank you. That's okay.
Mhm. Yeah, no problem. Sorry about that. All right. Anything else before we log out?
Hey, Professor Russell.
Yeah.
I need to talk to you something about that happened last semester.
Yeah.
Right
When
before
we supposed to talk yesterday at 10:30?
Yes, sir. I came to the Zoom meeting. Nobody was there.
All right. I got a class at 10. Let's say, are you free at 11:30 today?
I'm about to take a quiz right now. So yeah. Yes, sir.
All right. Just shoot me an email when you're free, and then I'll log in and we can talk. We can talk then.
All right. Thank you.
Okay. All right. If there's nothing else, I'll see y'all on Monday. Have a good weekend.
Thank you. Have a nice weekend.
All right.